All right, so we're going to continue our discussion of thermodynamics. Right, so before coming into this course, you would have discussed this topic of enthalpy, the heat that's exchanged with a system and its surroundings. We kind of expanded on that concept to introduce two new thermodynamic variables. The first of which is entropy. We spent a lot of time talking about entropy and things that were entropically favorable. Remember, when you think entropy, you think the energy of disorder, right? The universe likes disordered systems. And we talked a bunch about a bunch of different examples of what would entail entropically favorable chemical processes. One of these, before we move on, we're going to expand upon a little bit more. And this is this idea of aqueous solutions being more disordered than solids. Okay. And we're going to say that this is mostly true. Okay. For the most part, if you take a solid and you dissolve it into a solution, it does indeed create more disorder because those particles, let's just take a look at what that would look like. Create more disorder because in a solid, those ions are fixed in their position. And then when you take it and you dissolve it into water, they dissociate and they kind of freely float about in this very disorderly fashion. But there are a bunch of salts that we talked about, especially, in this past unit, we talked a lot about these insoluble salts. We learned about KSPs and how you can calculate how much of an insoluble salt actually dissolves in solution. And what we found was it's not much, right? It's usually a very small amount. So for those, why is it not entropically favorable to be placed into solution, right? So from the standpoint of the ions, there is indeed more disorder. Again, these ions are now all freely dissociating or have dissociated and are now freely diffusing around this solution. However, there's another component to a solution, and that's what happens to the solvent, right? And so what we see is when this positively charged ion dissociates, it attracts a bunch of water molecules to it, right? Because water's polar, so it's got this dipole moment going on. It's a different color here, right? Where that partially negative end of that water molecule is going to interact with that positively charged ion. And then if we look over at the negatively charged ion, we see sort of the same thing, but now our water molecules are flipped around and it's the partial positive end of that water molecule that's interacting with that ion. Okay. And so what happens is the solvent forms what's called a solvation shell. Oops. A solvation shell around those ions, where you have those water molecules all lined up interacting with those ions. And this solvation shell is entropically unfavorable, right? Because those water molecules, they used to be able to diffuse freely around that liquid. They would have any orientation they wanted, randomly kind of just tumbling about. And now all of a sudden you've taken them and you fixed them around this ion. You've created a bunch of order, right? So although there's this disorder associated with the ions dissociating and diffusing around the solution, there's also this orderly component of the solvation shell. So let's take a look at two specific examples here. Okay, so the sodium ion, we know that most sodium compounds are soluble. And so the sodium ion, when you take it and you dissolve it into water, it has a positive entropy. The entropy of this ion, let me actually get my little cheat sheet here. Right, has a positive entropy of 58.45 joules per Kelvin. All right, and again, entropy, when it's positive, that's a good thing. That's what the universe wants. That means more disorder. right? And so because sodium has a small solvation shell, taking sodium and dissolving it in water is entropically favorable. All right, but on the flip side, if we look at the calcium, not the calcium, I'm sorry, the phosphate ion, we know that most phosphates are insoluble compounds, and it turns out that the entropy of a phosphate ion is negative 220.5 joules per Kelvin. All right, and I'll show you how I get these values here in a second. Right now, you're just going to trust me on them. All right, and we can see that the phosphate ion has a negative entropy associated with it, and that's because the phosphate ion has a very large solvation shell, which is entropically unfavorable. All right, so for some salts, when we know that they're very soluble salts. So again, sodium compounds tend to be soluble. Those will be entropically favorable when you dissolve them into solution, and it's because they have a very small solvation shell. So the deep fusing of those ions throughout that solution in that random motion is good, entropically favorable. Some of our insoluble salts, the reason that they don't dissolve is because that process is entropically unfavorable, because although those ions can diffuse randomly about, they create these large solvation shells, which create a lot of order for those water molecules that used to be in the solvent, able to freely float about. Now they're kind of fixed to those ions. Okay, so that's why we had to add that little caveat there. Okay, so our whole point of discussing entropy was really to get at this here, this idea that we have what we call a chemical potential that's going to predict whether or not a process is spontaneous or non-spontaneous. And it had those two elements, the enthalpy and the entropy, both of which had to be considered in order to determine whether or not a process would happen spontaneously. This delta G, we called it a chemical potential, kind of in analogy to a mechanical potential from a physics class. The real name for it in chemistry, and that's what we're going to call it from now on, is what's called the free energy. Okay, and our free energy tells us that a process is spontaneous if and only if that delta G is less than 0. Right? So by looking at the delta G of a process, we can determine whether or not it's going to happen, whether or not it's spontaneous. So let's take a look at two chemical reactions, and I'm going to give you their delta G. Again, you're not going to know how I got this quite yet. We're going to build up to that. Right now, you're just going to trust me on it. All right. And we can see that one of these processes, one of these reactions is spontaneous and the other one is non-spontaneous. And what tells us whether or not it's spontaneous is simply the sign of that delta G. So in this first one, the delta G is positive, so that would be a non-spontaneous reaction. And in the second one, our delta G is negative, so that would be a spontaneous reaction. All right, so again, the sign of delta G is what we're going to look at to determine whether or not a reaction or any sort of a chemical process occurs spontaneously. All right, now, this world is full of reactions that are not spontaneous, that still occur, right? And a great example is biology. Life in general is a very entropically unfavorable thing. Think of how much order there is in your body right now, the cells, the sugars, all that sort of stuff. It's a highly ordered system. And if you think about it, the universe hates order, right? So the universe hates biology, hates life. I'm sure we're not alone out there in the universe, but to say the least, we are few and far between life in this universe, right? Very, very rare event that occurs. And part of what makes it so rare is that we need all these non-spontaneous processes to live. We need to be able to create proteins and store fats and all these other things that would be non-spontaneous. So how does the body do it? You can get away with a non-spontaneous process occurring as long as you couple it with a spontaneous process that's even more favorable. In the body, 99% of the time, that process is the hydrolysis of ATP, right? Our cells use ATP for energy. So what happens is it couples the building of proteins with which is an unfavorable event, with the hydrolysis of ATP, which is a very favorable event. By coupling those two reactions, it can make that non-spontaneous process occur. So what we're going to do is we're going to couple these two reactions here and determine whether or not by coupling them, we can get that non-spontaneous process to occur. So what do I mean by coupling? We're going to simply sum them up, the net result of performing both of these reactions simultaneously. So we're going to add up all of our reactants, which would just be the two waters plus the two carbon monoxides plus that oxygen gas. And now sum up all of our products, the two hydrogen gases, our oxygen, and our carbon dioxide. All right, but now we're going to look at the net effect of performing both of these reactions simultaneously. That means we're going to go through and cross out what appears on both sides and then write the net, write our result here. So, right, so two waters, gaseous waters, plus the two carbon monoxides give us two hydrogens and two carbon dioxides. And now how am I going to determine whether or not these coupled reactions happen spontaneously? I'm just like I simply summed up those two reactions and got the net result. I'm going to simply sum up those two delta G values in order to determine the delta G of the coupled reaction, which is in this case negative 57.2 kilojoules. So we can see that by coupling this non-spontaneous reaction with this even more favorable spontaneous reaction, we can get this net reaction that actually does occur spontaneously. All right, so now why was I able to just simply sum them up, those two delta G's, in order to get the delta G of the net reaction? Why didn't I have to do something more complicated than that? Well, this is because delta G, along with all the thermodynamic quantities that we learned about, are what are called state functions. Okay, so all of those thermodynamic quantities, the delta G, delta S, and delta H, are all state functions. And this is different than what's called a path function. Okay, and this is a little bit mathematically, from a mathematical standpoint, this is a little bit above our pay grade. For this particular course, this is something that it would take you quite a bit of math to get to before you would learn this concept in a math class. Nonetheless, we're going to introduce sort of it in a simplistic form using an analogy here. Okay, so what we're going to use is this analogy of, we got these hikers traveling up this mountain here, a red hiker, a green hiker, and a blue hiker. Okay, and you can see that they're all starting at the same point here, and they're all ending at the same point, but they take very different paths up that mountain. Okay, so a path function would be, an example of a path function would be the distance that these hikers traveled. We can see, let's just compare the two extremes, the red and the green. We can see that although they started in the same place and they ended in the same place, that green hiker took a beelined path directly up that mountain, right? So traveled a shorter distance than the red hiker, which took a little bit more of a meandering path back and forth, getting to the very top. So the path function here of distance, that depends and we could say the value depends on the path taken, right? Simply put, the green hiker traveled a shorter distance than the red hiker. Okay. But a state function would be the displacement of those two hikers. The displacement is simply a measure of where you started and where you finished, what that difference is. That's your displacement. And so regardless of the path taken, all of these hikers had the same displacement. They all started at the same place and all finished at the same place, right? So the state function does not depend on the path taken. It only depends on, we can say the value only depends on the initial and final states. In this case, those states were position. We're going to extend this by analogy to our thermodynamic functions. The bottom line is that it doesn't matter if I did this particular reaction in one step, or if I did it by combining these two steps here, or if I did it in 1,000 different steps. The overall net difference in free energy will always be the same. Okay, so it doesn't matter how many chemical reactions you couple together, the difference in free energy will be the same as if you did that in just one shot. Okay, so that's how we can simply add those up in order to get our delta G of our reaction, of our overall reaction, because delta G, along with our other thermodynamic variables, are state functions. And scientists have taken a wild advantage of this. They've taken advantage of this and created these tabulated values, these tables of these thermodynamic constants. Okay, so one of our part of our constants page for this chapter are these tables of all these thermodynamic variables. So let's look here at what we got. Right, so what we see is this giant table where what's listed at the top is the enthalpy, the free energy, and the entropy. Right, and we have that listed for a bunch of different compounds here. So let's focus on one here. We'll go to BF3. And what's actually tabulated here is the enthalpy, free energy, and entropy of what's called a formation reaction, where the reactants are the elements in their standard state. So boron's standard state is just all by itself as a solid. Fluorine's standard state is actually as a diatomic gas, and that creates our products BF3. And these formation reactions are always balanced in such a way that you just get one of your products. So in this case, I would have to balance that out with a 3/2 for my fluorine in order to make that all work out. Right, so we have all these tabulated values for this for these thermodynamic quantities of these formation reactions. But because we can kind of sum up the reactions the way that we just showed before, we can use these values to calculate the enthalpy, free energy, and entropy of any reaction. So let me show you how we do that. So we're going to look at a little bit more condensed of a version here and this particular reaction. And we're going to look at just the enthalpy and the entropy for right now. And I'll talk about why that is here in a second. Okay, so from this data here, I can get the delta H of the overall reaction. Okay, and what I want you guys to have in your mind when you're thinking of how to get these thermodynamic quantities, similar to when we're talking about equilibrium constants, you think products over reactants. For these, I want you to think products minus reactants. Right? Anytime you're going to do one of these problems, you just chant to yourself products minus reactants, and that way you know to set it up correctly. All right, specifically, if we're going to make this all mathematically symbolic, put it in this fancy math language here, what we would say is the delta H of the overall reaction is the sum of the delta H of the products multiplied by their stoichiometric coefficients that we get from our balanced chemical equation, minus the sum of all of the delta H of the reactants, again, multiplied by their stoichiometric coefficients. So what does this look like for this particular reaction? All right, so what I'm going to do is I'm going to take the enthalpy of my product and multiply it by that stoichiometric coefficient of 2. So 2 times negative 395.7. And then I'm going to subtract the sum of all my reactants in order to make sure that this minus sign gets distributed to all of those reactants. I'm going to make sure to put this term in parentheses. Okay, don't forget to do that or you won't get the correct value. So then I'm going to look up for my product. The first one is the sulfur dioxide. So look up that delta H value, multiply it by its stoichiometric coefficient. So 2 times the negative 296.8. And then I'm going to add on what it is for my oxygen, which is in this case just 0. Okay, so I actually wouldn't even have to include that term. But so summing this all up, I can see that the delta H of this reaction is negative 197.8. And if I look at my units, the units on this will be that I get from my table right here. So, right, I can always reference this if I don't know. My units are kilojoules. And the mole actually drops out when you multiply it by that stoichiometric coefficient. So my units here are just kilojoules. Right, so I can do the same thing for my delta S for this reaction. But now I'm going to use those values in the delta S column of my table. So again, looking it up for my products, now it's the 256.8 multiplied by 2. Again, I'm going to put those reactants in parentheses. Look up for my reactant here, multiplying that by its stoichiometric coefficient, so 248.2. And then summing it up for what it is for my other reactant. My oxygen, which is the 205.2. All right, and so we get that this is equal to negative 188. We look at our units. Joules per mole Kelvin. So the mole again drops out when we multiply it by our stoichiometric ratio. And so this is joules Kelvin. Okay. Now, one thing that I've sort of glossed over here up until this point is if we look at these values here, our tabulated values are delta H naught and entropy naught, that little circle on there. So what does that mean? That means that these values are tabulated specifically under standard conditions. Okay, so what does that mean? So basically, in order to create this massive table of all of these different thermodynamic variables, that was a work of a lot of scientists collaborating together. They all had to decide on a set of conditions to use, right? We had to decide like, what are our conditions for that I'm going to do in my lab? You got to do the same conditions in your lab. That way we can compare those values, right? So these are these standard conditions. Standard temperature and pressure is something you may have remember from last semester, STP. And so standard conditions would be 298 Kelvin, a temperature of 298 Kelvin. We'll talk a little bit more about the pressure as well as the concentration component of standard conditions next class. For right now, we're just going to focus on the temperature aspect. So all of these values are tabulated for conditions that are at 298 Kelvin. Okay. So first of all, let's just take a look at our results here. So again, this is our reaction, and this is what we got for our delta G and our delta S. And again, remembering that this is at 298 Kelvin. So first of all, looking at this delta H, we can conclude that this is an exothermic reaction because the delta H is negative, which is, from the universe's standpoint, good, right? The universe likes exothermic reactions because they release energy. And if we look at our delta S for this reaction, this is an entropically unfavorable reaction. And I can tell that by looking at the sign of my delta S. The delta S is negative. Negative entropy is bad. I could also tell that just without even looking at the numbers by looking at my balanced chemical equation here. This is a chemical equation that consumes 3 molecules of gas and only creates 2. All right. So remember, if you're creating fewer gas particles in a reaction than you're consuming, that's not going to be entropically favorable. Okay, so we talked a lot last class about being able to just look at a chemical formula and know whether or not the reaction is entropically favorable or unfavorable. So in this case, we could have predicted that this delta S was going to be negative just by looking at this chemical equation. All right, and so now we're going to combine these two into our delta G, because remember, delta G is the delta H minus T delta S, and we know what temperature these values are formulated at. The one thing that I'm going to caution about these calculations is that your entropy values are always tabulated in energy units of joules, whereas specifically joules per Kelvin, but the joules I'm focusing on right now, because the enthalpy values are calculated in kilojoules. And so in order to combine these in this equation, we're going to have to marry the two. And so what we're going to do is convert our entropy into kilojoules per Kelvin by dividing by 1,000. Okay, so when I plug this in here, I'm going to take my negative 197.8, subtract that temperature of 298 Kelvin, whoa, and then multiplied by the negative 188 over 1,000 for my my units of entropy to make sure that I've converted them to kilojoules. And so if we do this, we can calculate the delta G for this reaction as negative 141.8 kilojoules. Okay, and so we can see that at the 298 degrees Kelvin, this reaction has a negative delta G, and thus we can say it's spontaneous. And if I had my table, so, in the table that I showed you that we have on our constants page, there's actually another column for delta G. If I had just taken those delta G values and done this exact same sort of thing here, like I did to calculate delta H and delta S, I would have gotten this exact value. Okay. But there's actually a benefit to looking at the enthalpy and the entropy instead of just the free energy. The free energy that you would have calculated is only good at one temperature, is only good at 298 Kelvin. But by looking at the enthalpy and the entropy, we can predict what delta G would be at other temperatures as well. For this particular reaction, it's going to be kind of interesting because although this is an exothermic reaction, which is favorable, it's also an entropically unfavorable reaction, which is bad, right? And so what we learned about last class when we were looking at this delta G equation, we made this like cheat sheet table here. We can see that reactions that are exothermic but entropically unfavorable, they will be spontaneous at low temperatures, but they will become non-spontaneous at high temperatures, right? So if we go back to our example here, we saw that indeed it was spontaneous at the 298 Kelvin, but now we're going to crank up the temperature. So first of all, this calculation was again at 298 Kelvin. Now we're going to crank up the temperature and predict our delta G at 1200 Kelvin. All right, so again, we'll have that same delta G, delta H minus T delta S. We're going to use those same enthalpy values of 197.8, but now we're going to change our temperature to 1200 and same entropy value. Again, got to convert it to kilojoules. And if we do the math on this one, what we'll see is that the free energy is now 27.8 kilojoules. So as we increase the temperature, right, we pass this point where now all of a sudden our reaction is non-spontaneous. Okay, so again, you could calculate the delta G based on those tabulated values, but it's only going to be good for one temperature, and that's that 298 K. Or we could calculate the enthalpy and entropy and combine those into our delta G, and we can use those at any temperature. It is an approximation because there is a little bit of a dependence of these values here on the temperature. We treated them as if they were constant at all temperatures. They do change a little bit, but it's a pretty good approximation. So it's one that we're going to use. We're going to pretend like they're constant, the same value at all temperatures. All right, so what other cool things can we do with our delta G here? All right, well, let's take a look at another reaction, the boiling of water. Okay, so first of all, we can see that this is an endothermic reaction. Which makes sense. Those liquid water molecules need to absorb heat in order to break off and go into the gas phase. So these are endothermic reactions, but they're also entropically favorable because that gaseous state is more disordered than the liquid state, right? Again, something that we should be able to predict just by looking at that chemical equation. All right, and for these types of processes, we talked about how these processes that were endothermic but entropically favorable are going to be non-spontaneous at low temperatures, but then spontaneous at high temperatures. Okay, and so we're going to show that here with this reaction. And we all have so first of all, let's take a step back. We all know this. We have an intuitive sense of this, right? Water doesn't just boil at room temperature. You have to raise the temperature and then it will start to boil, right? So what we're going to do is prove that using our delta G, our thermodynamic variables here. Whoops. Right. And actually, before we do this real quick, again, because they have these knots, these tabulated values are really for at 298 Kelvin. Let's take a step back and remind ourselves of how we convert from Celsius to Kelvin. All right. Your temperature in Kelvin is your temperature in Celsius plus 273. It's really 273.15, and it's an exact value. I don't know why, but your textbook rounds off that 0.15. It drives me absolutely nuts, but because that's what your textbook does, and we're going to be consistent, we're going to say that it's Celsius plus 273.15. So then if my temperature at standard conditions is 298 Kelvin, we rearrange to solve for the degrees Celsius. We're going to subtract 273 from each side. we see that this would be 25 degrees Celsius, right? So 298 Kelvin is 25 degrees Celsius. Okay, so we're going to perform this first calculation at that standard conditions, that 298 Kelvin, which is again 25 degrees Celsius. And what do we think? Is water going to boil at 25 degrees Celsius? No. All right, so let's just show this mathematically. We're going to take our temperature, the 298 Kelvin, multiply it by that entropy, but again, make sure to divide that entropy value by 1,000 so that we can get our units into kilojoules. And so if we do this, we see that our delta G is 8.18 kilojoules. So that would be non-spontaneous. Which checks out, right? Water is not going to boil at room temperature. All right, well now let's crank up the temperature. And we're going to do the same calculation at 150 degrees Celsius, which would be, what is that? 423 Kelvin. So my delta G equals that same delta H minus now 423. And we see that my delta G is now negative 5.45 kilojoules. And so indeed, this reaction of the boiling of water will happen spontaneously at 150 degrees, which also checks out with what we know, right? Because now we're above that boiling point of water. All right, so now we're going to do one last calculation, but let's see what delta G is going to be at that boiling point, at that 100 degrees Celsius or 373 degrees Kelvin, or just Kelvin. Delta G equals that 40.657 minus 373 times the 109 over 1,000. And what we're going to find is the delta G is 0. Right? So this is a fairly interesting result that we're going to be able to take advantage of going forward. So let's just summarize what we've just learned, is that delta G equals 0 at the boiling point. All right, specifically the delta G of that boiling reaction, that vaporization reaction, is 0 at the boiling point. Okay, and really delta G is 0 at equilibrium. Sorry, the dog's found something. With this caveat that it's at equilibrium under standard conditions. And this is actually a pretty big caveat here, and we'll talk exactly about what this means next lecture. For right now, simply put, it means that you have equal amounts of that liquid and gas phase. Okay, so when you're at that melting temperature, when you're at that boiling temperature, you're at equilibrium between the gas and the liquid phase. If you were in this closed system, there would be equal amounts of both of them, right? So that's why delta G is 0 at the boiling point. But this is something that we can take advantage of to solve some interesting problems here. So now we're going to use this to figure out what the boiling point is of, in this case, cyclohexane. So cyclohexane is kind of this famous molecule in organic chemistry. If you've ever seen people doing organic chemistry, they tend to draw a lot of hexagons. Those hexagons represent cyclohexane. Okay, so what we're going to do is use the delta H and the delta S of this vaporization reaction, of this boiling reaction here going from liquid to gas, in order to estimate what that boiling point is for cyclohexane. Okay, and what we're going to do is we're going to take advantage of, we have our equation here, delta G equals delta H minus T delta S. And we know that at the boiling point, delta G equals 0. So now we can plug that into our equation. All right, and now if we rearrange, I'm going to take both sides of my chemical equation and I'm going to add the T delta S. So add T delta S over here, add T delta S over here. So now I have temperature delta S equals delta H. And then I'm going to get temperature all by itself by dividing both sides by delta S. That crosses it out over here. And so what I have built is this relationship that my temperature of, and specifically my boiling point, is equal to the delta H of that vaporization reaction divided by the delta S of that vaporization reaction. All right, so using our specific values for this compound here, we can plug that in. So temperature equals that to 29.97 divided by 84.7, but I need to convert that to kilojoules to marry my units here. And what we see is that my estimated temperature of boiling here would be this 353.8 Kelvin. If we wanted to convert that to something a little bit more meaningful, to convert that to Celsius, we would see, you know, subtract 273, we would see that this is 80, did I do, yeah, 80.8 degrees Celsius, right? So using the fact that delta G is 0 at the boiling point, I can then, if I'm given the delta H and the delta S of this vaporization reaction, I can use that to approximate the boiling point using that equation there. All right, so just some cool things we can do with our free energy, our thermodynamic variable. Cool.